300 million years ago, Earth looked like heaven. There were thick green woods, huge dragonflies flying through the air, and swamps that went on forever. But there was poison in this heaven. The trees could catch fire from the oxygen in the Carboniferous, millipedes got longer than people, and the air itself could kill you. It wasn't the time of dinosaurs or animals, it was much stranger. Welcome to the Carboniferous, which is a live, burning horror that looks like Eden. The forests that could kill you. If you go back 300 million years, you'll see a world that looks like heaven from far away. There is green all the way to the horizon, big trees rise 100 feet into the mist, and thick ferns cover the whole ground. But this wasn't just any forest. The Carboniferous jungle was hot, stuffy, and dangerous. Nature had built a living trap for the animals there. It was before animals, flowering plants, and even dinosaurs. Instead, tall club mosses, trees that spewed spores, and air that was so full of gases that one breath could choke you, ruled the world. The land was one giant swamp. Trees like lepidodendron and sigillaria grew straight and tall, their trunks covered not in bark, but in patterned scales. Their roots formed wide, webbed mats that tangled together, creating unstable ground. Beneath them, decaying plants piled up layer after layer, releasing methane and carbon dioxide. In some regions, the gas built up so thick that a spark of lightning could ignite the entire swamp. What looked like lush green paradise could turn into a suffocating pit or an inferno within minutes. The air was unusual. Because so many plants were photosynthesizing, the oxygen level went through the roof. But the air was also full of volatile organic compounds, which are chemicals that plants and dead matter give off when they break down. Scientists today, who study preserved plant spores, have found proof that these woods were full of harmful particles in the air. There were so many seeds from ferns and club mosses that they left behind thick layers of dust in the fossil record. Breathing in that fine powder would have made many small animals' lungs swell and killed them. Even frogs, which were the most common land animals at the time, may have had a hard time staying alive in these woods. The forest floor was a death trap. Beneath the roots lay peat bogs, soft, oxygen-poor mud that could swallow any animal that slipped. Fossil skeletons of early amphibians and arthropods have been found perfectly preserved in these deposits. Trapped mid-struggle, their bodies sealed under centuries of sediment. Every step could mean life or death. Sunlight barely reached the ground. The massive canopies of tree-sized ferns and horsetails blocked out most of the light, casting the forest in a permanent green twilight. It was warm, always wet, and filled with fog that never lifted. In that constant dimness, early creatures evolved to rely on movement and vibration more than sight. Some paleontologists believe this is why so many Carboniferous predators, like early amphibians and giant insects, developed exceptional sensitivity to sound and motion. You didn't see danger here, you heard it. The strangest part of this world was that it was alive in every direction. The trees themselves weren't like modern ones. They had no rings, no bark, and no deep roots. They grew fast and died faster, collapsing in great heaps that fed the next generation. Each fall released clouds of spores so thick they could block out the sky. Studies of fossil pollen layers show spikes of spore density during warm seasons, suggesting that the air itself turned yellow-green when these forests reproduced. To breathe during those times might have been nearly impossible for anything without specialized lungs or gills. But the Carboniferous jungle may have been most dangerous because it was unstable. Because the roots were not deep and the dirt was soft, it often gave way. Trees could fall at any time, killing the small frogs that lived below. Giant arthropods, some as big as dogs, ran over dead tree logs, eating moss and dead plants. Even though the environment was chaotic, everything was reused, buried, and born again, making the thick layers of carbon that would become the coal we burn today. Modern geologists studying coal seams from this period find traces of sulfur and methane bubbles trapped in the rock. proof that these swamps regularly belched toxic gases into the air. In small, low-lying basins, this could have created invisible pockets of suffocating air, where animals died silently, without a struggle. The oxygen overdose. It looked like the woods in the Carboniferous were living because they were breathing too much. During this time, the Earth's air levels were unlike any other time in history. About 21% of the air we breathe today is oxygen. This number went up to a record high of over 35% about 315 million years ago. That might sound like a gift to a person. In fact, this oxygen overdose made the world a bomb that was about to go off. The surge began with plants. As giant ferns and club mosses spread across the continents, photosynthesis worked overtime. These plants sucked in carbon dioxide and pumped out oxygen faster than volcanoes, and decaying matter could balance it. Normally, bacteria and fungi break down dead wood and return carbon to the air, but those decomposers hadn't fully evolved yet. The result was a runaway feedback loop. Plants trapped more carbon underground, oxygen levels climbed higher, and the air grew unnaturally rich. At first, life seemed to thrive. Insects, amphibians, and arthropods exploded in number. But higher oxygen also changed the rules of biology. With more oxygen available, animal metabolisms accelerated. Growth rates shot up. Some species evolved to gigantic sizes because their bodies could finally get enough oxygen to support larger organs. Dragonflies like Meganeura reached wingspans over 2.5 feet. Millipedes like Arthropleura grew longer than humans. Even scorpions and centipedes reached monstrous proportions. Yet what helped them thrive made the world hostile for everything else. Oxygen at such high levels is extremely reactive, meaning it fuels fire with terrifying intensity. A spark of lightning, a volcanic ember, even a falling branch scraping rock could set off uncontrollable wildfires. In the Carboniferous, fire didn't spread, it exploded. Scientists studying fossilized charcoal layers have found entire regions turn to ash again and again. Some of those coal seams still bear microscopic glass beads. Melted sand formed from temperatures exceeding modern forest fires. For creatures living there, even a small fire could turn deadly within seconds. Oxygen-rich air made flames leap higher and spread faster than any animal could escape. Imagine a world where lightning flashes once, and the forest canopy becomes an instant wall of fire. Amphibians hiding in mud burrows suffocated as flames consumed the oxygen around them. The air itself became toxic, filled with carbon monoxide and soot. The weather was also changed by high oxygen. The Earth got cooler because there was more oxygen in the air. Oxygen doesn't trap heat like carbon dioxide does. This helped make ice ages that moved forward and backward across the poles, freezing some parts of the world, while other parts burned with tropical woods. It was an odd mix for a world that was both full of green life and short of air. Modern scientists have tested what such an atmosphere would feel like. In lab simulations with higher oxygen, small fires become impossible to control. Even damp wood ignites instantly. Insects grow larger and move slower, their bodies limited by air pressure. And even though more oxygen sounds healthy, for living tissue, it's corrosive. Too much oxygen damages cells, a process called oxidative stress. For early animals, that likely meant shorter lifespans and frequent mutation. In fact, fossil evidence shows that some Carboniferous animals developed thicker exoskeletons, possibly as a defense against both predators and the harmful effects of the environment. High oxygen meant more energy, but it also meant more damage, a world of fast growth and fast decay. A new study from the University of Leeds looked at charcoal layers from Carboniferous coal beds and proved that the number of wildfires rose greatly when oxygen levels were at their highest. These results show that Earth's ecosystems were stuck in a dangerous cycle. Plants made oxygen, fires killed the plants, and then new plants grew from the ashes. It was a planet that was always starting over. Arthropleura, the 9-foot millipede that ruled the ground. The biggest land insect ever found, Arthropleura, would have been one of the scariest things to see in the Carboniferous woods. It moved slowly and deliberately. It was hard, segmented plates that made this thing look like a huge millipede. It was up to 9 feet long and almost 2 feet wide. Early insects and frogs saw it less as an animal and more as a wall of defense that could crush anything in its way. Fossils of Arthropleura have been found in Scotland, Germany, and the eastern United States, preserved in what were once swampy floodplains. The tracks it left behind, called Arthropleura ignites, are among the most dramatic fossils ever found. Each footprint is the size of a human hand, spaced in long, parallel lines where the giant millipede once dragged its many legs through soft mud. Some tracks stretch for over 6 feet, showing that this monster didn't just live here, it ruled the ground. At first glance, it looks like something from another world. Its body was made up of many metal plates that overlapped and protected it from danger. This allowed it to bend and twist through tight areas. It had hundreds of legs that all moved together perfectly, making a wave-like motion across the forest floor. It most likely made a loud rhythmic rustling sound when it moved, like dry armor scraping against leaves and wood. For a long time, scientists believed Arthropleura was a carnivore, imagining it feeding on smaller amphibians or insects. But fossil evidence tells a different story. No sharp jaws or piercing mouthparts have ever been found. Instead, it had simple chewing mandibles, more suited for grinding than tearing. This means it was most likely a herbivore, feeding on decaying plant material, fallen leaves and ferns. In a forest overflowing with vegetation, it never went hungry. Its size alone made it nearly invincible. With no large land predators in the Carboniferous, Arthropleura could move freely, unchallenged. Even early amphibian hunters like Eriops or Proterogyrinus would have been too small to pose a serious threat. The only things dangerous to Arthropleura were the unstable swamps themselves and fire. Fossils found in coal beds suggest that many individuals were killed when forest fires swept through, their shells burned and preserved in ash. The real reason for its huge size is the air around it. The Carboniferous air was full of oxygen, which made Arthropleura's lungs, or trachea, work much better than any modern bug could. Arthropods today have limits on how much oxygen they can move through their bodies. But in a world with 35% oxygen, those limits didn't exist. With each breath, the air fed its body, which helped it grow into a huge monster. New studies have added interesting aspects to our knowledge of its biology. In 2018, paleontologists found a piece of an exoskeleton in northern England. It was over 2.5 feet across, and it was most likely from a person who was about 9 feet long. There were signs of an exoskeleton that was dark and shiny, probably with stripes to help it hide. These were found in the armor that had been kept. In spite of its size, this means that Arthropleura may have mixed in surprisingly well with the dark green atmosphere of the Carboniferous forest. Yet even this gentle giant had to survive in a dangerous world. Forest fires could sweep through without warning, collapsing trees and turning its home into a furnace. Swamps filled with methane could suffocate it in seconds. And when the climate began to change toward the end of the period, drying out the wetlands, Arthropleura's reign ended. Its huge body needed humidity to breathe. Without it, its tracheal system would have dried out. By the beginning of the Permian, both the giant millipedes and the woods that had supported them were gone. Its smaller offspring, like millipedes and centipedes, are not even close to being as powerful as it was. Even so, every time paleontologists find one of those long preserved tracks, it tells the same scary story. The ground seemed to move in the past. Meganeura, the sky's flesh-eating dragonflies. At that time, the ground was ruled by giant millipedes, and the sky was ruled by Meganeura, which was the biggest flying bug ever found. With wings that were up to 2.5 feet long, these dragonflies were the scariest birds in the air. They would swoop through the thick, misty woods looking for food. It's hard to believe how big they were, but they looked a lot like dragonflies today. Their wings were longer than a hawk's, their eyes were as big as golf balls, and their mouths were sharp enough to cut through amphibian skin. Fossils of Meganeura have been discovered in France, England, and the United States. perfectly preserved in fine shale from ancient swamps. Each fossil reveals the same structure seen in modern dragonflies. Long, transparent wings supported by intricate veins, a segmented body, and a head with enormous eyes. Those eyes gave Meganeura near-perfect 360-degree vision. In a world packed with giant insects and small amphibians, that meant nothing could hide for long. Meganeura wasn't big by coincidence. The Carboniferous climate made it that way. The air was full of oxygen, which helped insects grow to amazing sizes. Their simple way of breathing, which was made up of a network of air tubes called trachea, could get them a lot more oxygen than insects can today. Scientists think that Meganeura would not be able to even take off if it were brought into our modern atmosphere, which has 21% oxygen. Its ideal home was the Carboniferous sky, which was full of air and sound. This predator was fast, agile, and ruthless. Its mouthparts were designed for cutting and chewing meat, not sipping nectar. There were no flowers yet, no pollination, no sweetness in the air, only the hunt. Meganeura preyed on smaller flying insects, juvenile amphibians, and anything else it could catch. Some scientists even suggest it hunted in groups, patrolling the skies above swamp clearings like living drones. Fossil evidence of bite marks on smaller insect wings supports the idea of intense aerial predation. Visualize that you are in the Carboniferous forests, and the air is heavy and still. All of a sudden, you hear a deep metallic buzzing. In the dim light, wings flash as a shadow goes by above. Then another. A group of huge dragonflies jumps through the trees in an instant, grabbing things in the air and disappearing back into the sky. It wasn't just loud. The Carboniferous was filled with the sound of wings. To modern eyes, Meganeura looks almost too advanced for its time, but its body plan is ancient. Dragonflies appeared early in Earth's history and changed very little afterward, proof of how perfectly designed they were. Their eyes could detect the slightest movement, and their flight control, using 4 independent wings, made them among the most skilled flyers ever to exist. They could hover, dart sideways, or dive straight down at incredible speeds. In today's terms, Meganeura was an attack helicopter in the age of ferns. Its larvae, called nymphs, were just as fearsome. They lived underwater in Carboniferous swamps, equipped with sharp jaws and spiny limbs. These aquatic predators waited motionless beneath decaying plants, lunging at anything that came too close, from tadpoles to early fish. Fossilized tracks and preserved mud casts show that Meganeura's young could grow up to a foot long before emerging as adults. New research using wind tunnel simulations has even shown that the dense air of the Carboniferous gave large insects an aerodynamic advantage. The thicker atmosphere created more lift with each wing beat, allowing creatures like Meganeura to glide with little effort. This may explain why such large flying insects could dominate the skies, something impossible in modern conditions. But even these aerial titans had weaknesses. Their size made them vulnerable to fires. When wildfires raged through the coal forests, the heat and smoke suffocated them mid-air. Climate shifts near the end of the Carboniferous also thinned the atmosphere's oxygen, slowly grounding these giants forever. The closest live cousin to them now is the dragonfly, which is smaller but still very dangerous. Seeing one hover over a pond takes us back to a time when their ancestors ruled the air with blades instead of wings. The swamps of fire. And during the Carboniferous, the Earth got more air than ever before. That made it burn like it had never burned before. The huge coal swamps that covered the continents were full of trees and plants that grew and died quickly. They were both lush and dangerous. But death meant something different in a world where oxygen made up more than 35% of the air. The woods did more than just catch fire when lightning hit. They went off. Modern scientists studying charcoal layers from this period have found something extraordinary. Continuous seams of burned plant material extending for miles, stacked through the rock record. This means wildfires weren't rare disasters. They were constant. Some paleobotanists describe the Carboniferous landscape as a planet perpetually smouldering. The air was so oxygen-rich that a single spark could ignite even damp vegetation. Once a fire began, it moved fast, racing along the tree canopies like a fuse. The trees themselves were part of the problem. The great lycopsids, Lepidodendron, Sigillaria, and Calamites, were built like rockets, tall, thin, and packed with resin. Their hollow interiors and dry outer layers acted like chimneys once ignited. When they burned, they didn't collapse quietly. The pressure from trapped gases sometimes blew them apart, scattering flaming debris for hundreds of feet. Scientists have found fossilized fragments of these trees fused into coal. The remains of forests turned to ash in seconds. Picture yourself in one of these swamps as the sky gets darker and the first lightning strikes. The air would hum, full of life force. Then there was the strike, and green turned red in an instant. The flames are taller than the trees. Clouds of smoke form that block the sun. Everything would be drowned out by the sound of the fire, and in minutes the rich jungle would turn into an oven. Animals ran into ditches or the ground to hide, but it wasn't safe there either. When fires go out, they leave behind areas of choking carbon dioxide that can kill quietly for a long time after the flames are out. Modern fire ecologists studying ancient charcoal have found microscopic silica beads, melted sand created by extreme heat. This means Carboniferous fires burned hotter than anything we see in nature today. Temperatures may have reached over 1,200 degrees Celsius. The aftermath was equally devastating. After each blaze, rain poured down, turning ash into black sludge. That sludge buried plants, animals, and even entire root systems, creating the massive coal seams we mine today. These cycles of fire and rebirth defined the era. The same forest that created oxygen fed the flames that destroyed them. And after every burn, new growth sprang up, feeding the process again. It was an ecological loop of creation and destruction, an endless combustion engine driving Earth's evolution. Fossilized plant spores show evidence of repeated exposure to smoke and heat. Their outer shells, known as sporopollenin, are often blackened or distorted, signs that the air was constantly filled with ash. Some scientists believe that this forced evolution among plants, favoring those that could grow faster after burns. Others think it pushed amphibians to develop tougher lungs, able to survive in smoke-choked air. The atmosphere had wounds on it as well. Studies of Carboniferous rock layers show that the amount of air changes at times that are exactly the same as times when there are big wildfires. A lot of carbon burned during firestorms in the woods, which made the oxygen level drop sharply. Then, when more wood grew, oxygen levels rose again. The world breathed in and out with the beat of death. The way life developed on land may have been changed by these fires. By cutting down large areas of forest, they made open spaces where snakes, which were still evolving at the time, could do well. Reptiles were able to live in burned, dry areas, where frogs couldn't because their skin was dry and scaly, and their eggs were hard to break open. In this way, every Carboniferous fire made way for the people who would run Earth today. Still, it's hard to say enough about how scary it is to live through one. Heat, a wave of air so hot it could boil small lakes, would have come before light. The smoke would block the sun for days. When it finally rained, it brought acid and ash with it, and covered everything in black mud. Amphibian apex predators, the crocodile frogs of the Coal Age. During the Carboniferous period, rivers and swamps were home to huge frogs. This was a long time before reptiles or dinosaurs ruled the land. These frogs and salamanders were not like the ones we know today. They were armored, muscled hunters that breathed through their lungs and had the strength of a crocodile and the hunger of a shark. Their territory was the dark rivers that wound through the coal woods, making it hard to tell the difference between land and water. Among the most fearsome was Eriops, a broad-headed amphibian nearly 10 feet long with a mouth packed full of sharp, backward-pointing teeth. Fossils found in Texas and New Mexico show it had thick, bony limbs capable of supporting its weight on land. It probably spent most of its time lurking in shallow water, ambushing anything unlucky enough to pass by, fish, smaller amphibians, even juvenile Arthroplura millipedes. Its skull was heavily built, with muscles strong enough to crush bone. When it bit down, nothing escaped. Other predators, like Proto-mammals, were sleeker and faster. Long-bodied amphibians that looked more like eels crossed with crocodiles. They swam through swamps using serpentine motions, snapping at prey with lightning-fast jaws. Fossils of Proto-mammals have been found in what used to be tropical river systems in Scotland and North America, proving that these beasts dominated both hemispheres. Their bodies were covered in overlapping scales, and their eyes were positioned high on their heads, the perfect design for waiting motionless under the water's surface. The Carboniferous environment made amphibians the kings of predators. There were no true reptiles yet, and no large land-dwelling carnivores to challenge them. The world's rich wetlands gave them everything they needed: warm water, abundant food, and endless breeding grounds. Many of these giants laid their eggs in shallow pools, surrounded by giant ferns, just like modern frogs, but their tadpoles were miniature monsters, already equipped with teeth and predatory instincts. Fossil evidence from Nova Scotia shows entire clusters of small amphibian skeletons preserved inside fossilized tree trunks, suggesting they hid in hollow logs or flooded stumps, waiting for prey. Unlike modern amphibians, many Carboniferous species had armored skin reinforced with bone plates called osteoderms. This made them nearly invulnerable to the claws and bites of smaller creatures. Combined with lungs that allowed them to gulp air and survive short periods on land, they were perfectly adapted for an unstable world of floods and fires. When fires tore through forests, amphibians could retreat into rivers and wait it out. When droughts came, they buried themselves in the mud until rain returned. Paleontologists studying their fossils have even found clues about their behavior. The limb bones of Eriops show dense growth rings, evidence that they lived long, slow lives, growing steadily year after year. In contrast, smaller species show faster bone growth, suggesting they matured quickly and reproduced often, a strategy for surviving in volatile ecosystems. These details paint a picture of a hierarchy, giant amphibians ruling the rivers while smaller ones darted through the undergrowth, filling every available niche. The Carboniferous was a dangerous place to swim. The rivers were clogged with fallen trees, bubbling with methane and decaying vegetation. Visibility was almost zero, and the water's surface was often covered in mats of floating plants. For smaller animals, that meant entering an Eriops territory without seeing it until too late. The ambush would have been instant: a flash of teeth, a burst of bubbles, and silence. Some scientists believe that these amphibians were the first top predators in land environments that were vertebrates. They showed that animals could live in both water and land, which made it possible for snakes to evolve. At the end of the Carboniferous, however, the weather became dry, wetlands shrank, oxygen levels dropped, and amphibians lost their habitat, which was their best defense. The bigger species would die out without constant lakes. They either went extinct or changed into smaller, more flexible forms, making room for early lizards that could breed without water. Even so, their remains show us how cruel their rule was. Small bones with deep bite marks, heads that have been crushed, and even fossilized droppings full of bone pieces show that the Carboniferous environment was not soft. In that world, even amphibians were thought to be scary. Insect empires, the reign of the arthropods. During the Carboniferous, people didn't live on land or in animals. Insects did. Things that lived in the woods, swamps, and skies back then looked like they were from a bad dream. Now was the age of arthropods. Things with 6 legs got as big as birds. Scorpions walked the forest floor longer than a man's arm, and the buzz of huge wings seemed to liven up the air itself. In the oxygen-rich atmosphere of the Carboniferous, insects reached monstrous proportions. Without limits on body size from oxygen supply, arthropods expanded into every available niche. The canopy teemed with flying predators like Meganeura, the dragonfly with a wingspan wider than a hawk's. On the forest floor, Arthropleura, the 9-foot millipede, dominated the leaf litter. And in between, a whole empire of lesser-known giants thrived. Roach-like Archimilacris, mantis ancestors, beetle forebears, and strange flat-bodied hunters that looked like a mix between a spider and a crab. These insects weren't just big, they were everywhere. Fossil evidence from coal seams across Europe and North America shows vast communities of arthropods, thousands of species living in the same forest systems. The Carboniferous jungle was a layered ecosystem. High in the canopy lived the flyers and gliders. On the trunks, armored, beetle-like insects burrowed into bark. And in the damp underworld below, centipedes, cockroaches, and scuttling predators swarmed through the detritus. The abundance of insects changed everything. With so many species feeding, decomposing, and breeding, the Carboniferous ecosystem became one of the most efficient recycling systems in history. Dead plants didn't always decay properly. There weren't yet enough bacteria or fungi to break down cellulose, but insects helped shred the debris. In doing so, they accelerated the burial of carbon-rich matter that later formed the planet's coal. Every piece of coal we burn today carries the imprint of their jaws. Some of these insects developed adaptations seen nowhere else in nature. Giant cockroach ancestors could glide short distances using broad wings. Early stick insect relatives camouflaged themselves as fern fronds. A group of primitive mantis-like predators evolved grasping forelegs, allowing them to snatch prey from mid-air. Their eyes were already complex, capable of detecting motion in the thick green twilight of the swamps. Also, insects were at the top of the food chain for the first time on Earth during the Carboniferous. They were food for many amphibians, but some bug groups turned into predators. Large ground hunter arthropods with sharp teeth and leg spines with serrations have been found in fossils. This suggests that they actively hunted smaller insects and even frog hatchlings. It was a bug world, and they were both making things and destroying things there. Evidence from fossilized amber-like resins, though extremely rare from this period, shows that insects already had complex life cycles. Some species likely lived in colonies or small social groups, building primitive burrows and nests in rotting logs. This early cooperation foreshadowed what ants and termites would perfect millions of years later. Even simple communication, vibrations, chemical trails, or light reflection may have evolved here first. But there were also risks in this kingdom. The air that made bugs so big also made them easy for fire to spread. A lot of flying insects died in the smoke when the coal ponds caught fire. Wing fossils that were formed in mid-flight can sometimes be found in Carboniferous coal layers. Still, insects were strong. Their eggs survived in the mud, and the woods were buzzing again in a few weeks. Scientists studying the Carboniferous fossil record often remark how alien these forests would have sounded. With giant crickets rubbing their armored legs, cicadas clicking, beetles droning, and dragonflies thrumming overhead, the noise would have been deafening. Acoustic modeling of fossil insect wings suggests frequencies between 3 and 5 kHz, similar to today's crickets, but far louder given their size. For any creature living there, silence simply didn't exist. Bugs were in charge of both life and death in this world of constant motion. They broke down trees, reused dead bodies, and filled every part in the food chain. They built things, scavenged for food, and killed each other. Their whole society was based on chitin and instinct. Toxic air and deadly fungi. It might have looked like heaven in the Carboniferous world, with its endless green cover, but there was poison below that beauty. You could die from the air you breathed. The ground you walked on could breathe out death. There was also a strange new enemy that grew as the trees grew, killer fungi, and toxic gases that turned the bogs into huge chemical traps. It started with abundance. Every year, entire forests of club mosses, horsetails, and ferns grew, died, and fell where they stood. But the world still lacked modern decomposers, the bacteria and fungi that today break down cellulose and lignin. As a result, the planet became choked in its own leftovers. Dead plants piled up in peat bogs hundreds of feet thick, sealing away carbon and trapping heat. In the stagnant, oxygen-poor mud, chemical reactions began to brew. When paleobotanists studied coal beds from the Carboniferous, they found evidence of gases trapped in ancient sediments: methane, carbon dioxide, and hydrogen sulfide. These were byproducts of half-rotted vegetation fermenting beneath the swamps. Methane, lighter than air, sometimes bubbled up in pockets that ignited with lightning. But hydrogen sulfide was worse, a gas that smells like rotten eggs and kills in seconds. It seeps upward, invisible and silent, displacing oxygen. Whole areas of forest floor may have been deadly without warning. This nasty mix not only made the air dirty, but it also changed the course of evolution. Animals that got too close to bogs that were breaking down were often found dead, with their bodies still in the black mud. Fossilized amphibians found in Illinois' Mason Creek rocks look like they died of suffocation and are completely whole. Geologists who are studying these places think that many of the inhabitants who died were poisoned by gas, not by animals. The rise of simple fungi began to change everything. Early fungal species, such as proto-taxites, had existed for millions of years before, but during the Carboniferous, new forms began experimenting with how to break down wood. Fossilized filaments found inside plant tissue show the first signs of white rot fungi, the kind that can digest lignin, the tough compound that gives trees their strength. These fungi were primitive, but they were the beginning of something revolutionary. They were learning how to eat forests. As these decomposers spread, they released massive amounts of carbon dioxide back into the atmosphere. In the short term, that increased the greenhouse effect, trapping more heat and humidity. In the long term, it destabilized the perfect balance that had made the Carboniferous so lush. The forests were, in effect, fueling their own destruction, creating the gases that would one day help end their era. It was weird to take in the air itself. The mix would not have been steady because oxygen levels were at all-time highs and carbon dioxide was bubbling up from the swamps. Flash oxidation, which makes clouds of carbon monoxide, could be caused by even small fires. Animals would die from that gas, which they couldn't see or smell, before they even knew they were in danger. You could fall asleep next to a bog and never wake up in this world where the atmosphere could turn against you. Some scientists think these conditions created localized dead zones, patches of forest where the combination of gases and decaying matter made survival impossible. In modern peat bogs, similar gases still kill wildlife today. During the Carboniferous, these zones could have stretched for miles, creating a checkerboard of life and death across the swamplands. The first fungi that adapted to break down wood left a chemical fingerprint still visible today. In the late Carboniferous, the rate of coal formation suddenly declined. That's because fungi had finally evolved the ability to decompose plant matter before it fossilized. The planet's biggest carbon trap began to close. In a sense, fungi ended the coal age, turning a world of eternal forests into one of decay and recycling. And with them came disease. Some paleontologists believe that early fungal infections helped regulate insect and amphibian populations. Microscopic traces found in fossilized amphibian bones suggest parasitic fungi had already learned to infect living tissue, a haunting preview of what would later devastate amphibian species millions of years later. It was a garden and a cemetery at the same time. Every breath was a risk, and every pool could be a trap. The gases that made coal also killed all the living things that were there, and the first fungus that developed to eat dead things set the stage for the next big change in life. The coal swamps that swallowed everything. Those who walked across a Carboniferous swamp would have been standing on death that looked like land. It wasn't a solid jungle floor, it was just a thin skin stretched over a slow living pit. What was under a mess of roots and plants was black water and peat, ready to sink anything heavy or unlucky. Back then, the ground could really eat you. These were the coal swamps. vast wetlands stretching from what is now North America to Europe and Asia. Their still waters were thick with decaying plants, fallen trees, and the half-rotted bodies of animals. The humidity never broke. Day and night, fog clung to the canopy, feeding layer after layer of moss and algae. Every time a tree fell, it disappeared into the muck, sealing its carbon-rich body beneath younger growth. Over millions of years, those trapped forests were compressed under pressure, forming the coal seams that now power our modern world. But in their time, the swamps were deadly traps. Fossils from sites like Mason Creek in Illinois and Joggins in Nova Scotia reveal amphibians, insects, and even tree trunks preserved whole, buried almost instantly by silt and vegetation. Some skeletons are found in lifelike poses, legs stretched upward as though clawing for the surface. It's clear they didn't just die there, they were swallowed. These bogs formed in low-lying floodplains where rivers overflowed and rainwater pooled faster than it could drain. The surface was covered by dense mats of plants, lepidodendron, sigillaria, and giant ferns, whose shallow roots held the muck just enough to look solid. Step on one of those mats and your weight might break through into soft peat below. Once trapped, even a strong animal couldn't escape. The thick mud and lack of oxygen made swimming impossible. Within minutes, the body sank and vanished beneath green water. This slow burial was perfect for fossilization. The lack of oxygen stopped bacteria from decomposing tissue, turning animals and plants into natural time capsules. When paleontologists cut open coal nodules today, they sometimes find delicate details. The texture of skin, the imprint of wings, even the fine veins of leaves. These are not just fossils, they're snapshots of suffocation. For early amphibians, these swamps were both home and hazard. Many species laid their eggs in shallow pools, not realizing that those pools could seal shut overnight with fresh plant matter. Fossil egg clusters and juvenile skeletons have been discovered buried together, entire generations trapped at once. Scientists believe sudden storms and flash floods were frequent, washing debris over living creatures and entombing them instantly. The same processes that killed also built the world's greatest store of carbon. Each fallen tree, each drowned creature, became part of the accumulating peat. Over millions of years, the weight of new sediment above compressed it into coal, dense carbon-rich rock that still burns today. Chemical analysis shows that this process locked away vast amounts of carbon dioxide, dramatically lowering the planet's greenhouse gases. Ironically, it was this natural carbon capture that helped trigger the Ice Age that ended the Carboniferous. The Earth had buried too much of its own fuel. Some of the most terrifying fossils can be found in the cliffs of Nova Scotia, where old tree stumps have been kept. These tree logs are hollow and used to stand straight in the swamp. Animals like small amphibians, early reptiles, and insects that sought cover there and never got out have been found by paleontologists. A famous find included several bodies buried together in a single stump by rising water and silt. These natural graves show that there was a world that made life and killed it at the same time. Even the air above the swamps was dangerous. Methane and hydrogen sulfide bubbled from decomposing plants, forming flammable clouds. A single lightning strike could ignite the surface, setting the peat ablaze while the deeper layers continued rotting below. Fires burned for weeks underground, releasing smoke that rolled through the jungles like fog. When rain came, it doused the flames and buried the ashes, another layer of carbon sealed for eternity. The energy that runs towns and factories today comes from the same old deaths. Every piece of coal is a piece of the Carboniferous swamp, which is made up of squished sunshine, fossilized trees, and the remains of things that sank and never came back up. The Seas of Terror. At that time, the land was like a swampy jungle, and the seas were even worse. They were huge, dark pots full of monsters. These were scary seas that were shallow and green, full of algae, silt, and ancient predators that lived there before fish or sharks looked like them. Below the surface, it was hard to see. The pressure was off. and the food chain was based on sneaking up on and protecting yourself. During this period, much of what's now North America and Europe was underwater, flooded by warm inland seas. These oceans were rich in life, but they weren't peaceful. Fossil beds in places like Montana, Scotland, and the Czech Republic reveal an underwater world packed with trilobites, early sharks, ammonoids, and giant sea scorpions, eurypterids that could reach the length of a man. The seafloor was littered with shells and corpses, and the constant decay made the water acidic and low in oxygen near the bottom. Anything that sank often never came back up. It was the Stethecanthus, a primitive shark with a flat, spiny anvil on its back that scared people the most. Scientists are still not sure what it was used for, maybe to show off for mates or for defense. But one thing is clear, this shark had a weapon. It had sharp teeth and rough, hook-like scales on the inside of its fins. When fish and amphibians got too close to the shore, it would hunt them in the shallows. Smaller cousins, like Cladocelache, had developed speed instead, making them fast hunters in the shape of torpedoes that could strike and disappear in an instant. Lower in the water, trilobites crawled like armored bugs, filtering nutrients from the sand or scavenging dead animals. Some species had spiny heads and tails for defense, while others could roll into tight balls, just like pillbugs today. Yet even this defense wasn't enough against the true monsters of the sea, the eurypterids. These sea scorpions were among the largest arthropods ever to exist, some over 8 feet long, with claws strong enough to pierce the armor of trilobites or tear fish apart. Their fossilized tracks in ancient tidal flats show that some even crawled onto land, the first known marine predators to do so. The water made things more terrifying. A lot of biological matter washed into the seas because plants were doing so well on land. This led to green blooms, which ate the minerals but took oxygen out of the water. That made anoxic zones along the coast, places where oxygen levels were so low that almost nothing could live. Animals and fish that got lost in these areas just died of suffocation. After a while, their bodies piled up in layers that turned into the black shale rocks that scientists study today. It was shocking how green and dim the light was underwater, coming through thick algae and whirling silt. Many predators couldn't see because of the steady haze, so evolution preferred other senses like chemical tracking, vibration detection, and electroreception. Early forms of these systems were made by sharks, which could pick up on movement and weak electric signs from prey that was hiding in the mud. The Carboniferous seas became a place where fear itself developed because of this race to improve our senses. Coral reefs, different from modern ones, flourished in some areas, built by rugose corals and bryozoans, but even they were temporary. The sea level shifted constantly as glaciers grew and melted on the southern supercontinent Gondwana. When ice sheets expanded, coastlines retreated. When they melted, oceans surged inland again, flooding forests and burying them beneath new sediments. Each cycle erased ecosystems and forced survivors to adapt or die. There was a strange animal in these waters called the helicoprion. It was related to sharks and was known for having a spiral-shaped mouth full of teeth. In the Carboniferous, its ancestors already had the first signs of this scary adaptation, a buzzing mouth that could cut through soft-bodied food. It would come to rule later times. Even the smallest creatures could be deadly. Early jellyfish drifted in clouds, their stinging tentacles almost invisible in the green water. Nautiloid relatives hunted by jet propulsion, snapping at anything that moved. The Carboniferous seas weren't just dangerous. They were claustrophobic, packed so tightly with life that every movement risked triggering a chain of attack. Layers of fossilized fish that looked like they all died at the same time were found by scientists. The fish may have been caught in quick periods of low oxygen or in storms that mixed up deadly sediments. These large-scale deaths show how unstable this world beneath the water was. It was easy to get by, but life was rich. Eurypterids, the first monsters to crawl onto land. A critter called the eurypterid, or sea scorpion, was the first to move out of the swamps before amphibians did. These were not small arthropods that were scuttling. Some species were almost 8 feet long, from head to tail, and had sharp, hooked claws that could crush fish. They were the first big hunters in the seas, and they may have been the first to come to land. Eurypterids appeared long before the Carboniferous, but this was their final and fiercest age. Fossils from Scotland, New York, and Estonia reveal species that dominated rivers, estuaries, and shallow seas. They were built for both speed and stealth. Broad paddle-like limbs for swimming, serrated pincers for trapping prey, and heavy armor that made them nearly indestructible. When you imagine a scorpion, double its size, take away its sting, and add the body plan of a lobster, that's a eurypterid. These predators ruled by ambush. Hiding in mud or sand, they waited for anything small enough to grab, fish, trilobites, or even other eurypterids. Their sharp claws left distinct marks on fossilized fish bones, confirming their hunting style. Some species, like Hibbertopterus, were so large they could have pinned an early amphibian underwater. Others were built for speed, capable of propelling themselves forward with rapid sweeps of their swimming paddles, gliding silently beneath the surface before striking like underwater spiders. What makes eurypterids extraordinary is that they may have been the first animals to explore dry land. Fossilized trackways, long drag-lined impressions, have been found in ancient tidal flats in Scotland and Pennsylvania, showing the distinctive footprint pattern of these creatures. These traces suggest that eurypterids could haul themselves out of the water for short periods, perhaps to hunt stranded prey, escape predators, or migrate between pools. They likely breathed using book gills, structures similar to those of modern horseshoe crabs, which could absorb oxygen as long as they remained moist. Scientists studying these tracks have reconstructed how the giant arthropods might have looked in motion, their bodies swaying side to side, claws digging into the mud for traction, tails dragging behind like anchors. In some ways, they were rehearsing evolution's greatest performance, the transition from sea to land, millions of years before vertebrates managed it. Their appearance alone would have been nightmarish. Picture standing beside a Carboniferous lagoon, the air thick with mist, when the surface begins to ripple. A dark shape rises, water cascading off its shell. The creature's eyes gleam with reflection as it drags itself ashore, claws opening and closing in silence. For a few moments it pauses, alien, ancient, unstoppable, before sliding back into the water with a hiss. The eurypterid's body design was brutally efficient. Its front limbs were modified into pincers for grabbing and tearing, while its rear limbs were wide paddles for swimming. The segmented tail, or telson, ended in a flat blade that acted like a rudder, or in some species, a weapon. Fossils show breakage patterns, suggesting that males may have fought each other, slashing with their tails or grappling in shallow water. These fights were part of a bigger story about evolution. Early sharks and eurypterids were fighting to be the best, and eurypterids held their ground for millions of years. They were still the top hunters in freshwater rivers and coastal ponds, where their shells still molt in layers that look like skeletons today. Scientists have found thousands of exoskeletons grouped together in some old deposits. This shows that they met in large groups to molt or reproduce, like crab swarms in the past. But their success had a limit. The same environmental changes that gave rise to amphibians and reptiles began to shrink their world. As the Carboniferous wore on, climates became less stable. Swamps dried up, sea levels dropped, and many shallow habitats disappeared. Sharks grew faster and smarter. Amphibians started hunting near shore, and oxygen levels in water fluctuated dangerously. For creatures that needed both land and sea, the planet was no longer kind. By the end of the period, eurypterids were in retreat. The giants vanished first, leaving only smaller, crab-sized species that clung to coastal marshes. Eventually, even they were gone, victims of the new ecosystems they had helped shape. The horseshoe crabs that live on beaches today are the closest living cousins. They are small, harmless, and very old. They are live memories of a time when their ancestors were the most dangerous killers. The unstable climate, ice, fire, and floods. For millions of years, the Carboniferous world looked like it could not be stopped. There were endless trees, air that was supercharged, and animals that were bigger than ever. But the planet was starting to move below that green surface. The temperature of the Earth, which used to be safe and warm, became unstable. From the south, ice crept in, the seas rose and fell like breath, and the woods that had kept people alive began to fall apart in waves of fire and flood. As the Carboniferous wore away at heaven, it did so with great care. The first cracks appeared in the southern supercontinent Gondwana, where massive ice sheets began to form. These glaciers grew thousands of feet thick, spreading across what is now South America, Africa, and Antarctica. At the same time, the northern continents, Laurentia and Euramerica, baked under tropical heat. This strange mix created extreme climate contrasts, freezing poles and steaming equator. For the first time in Earth's history, true ice ages and tropical monsoons coexisted. Scientists know this from glacial deposits found alongside coal seams, an impossible combination unless the planet was seesawing between cold and warmth. During cold phases, sea levels dropped by hundreds of feet, exposing vast continental shelves. Rivers cut deep valleys into the land, and coastal ecosystems died off. When the glaciers melted again, all that water rushed back, flooding the continents in catastrophic surges. Forests drowned, swamps vanished overnight, and salt water invaded freshwater systems. Fossil evidence from Kansas and Scotland shows entire layers of Carboniferous forest buried beneath marine sediments, then covered again by new forests. Each layer represents a cycle of destruction and rebirth, one that could happen in as little as a few thousand years. Imagine a world where the coastline moved dozens of miles back and forth within a single lifetime. One generation might be born in a swamp, the next would live above an ocean floor. Chaos broke out in the atmosphere because of the changes in temperature. Cold winds from the glaciated south met warm air near the equator, which kept the storms going. Lightning struck almost every day, setting oxygen-rich woods on fire over and over again. Each fire put more carbon dioxide into the air, which warmed the Earth for a short time until new plants grew and sucked up the carbon, which cooled the planet down again. Because of this feedback process, the Carboniferous was one of the most unstable times for climate ever known. Geologists studying oxygen isotope ratios in fossil shells have mapped these swings in astonishing detail. Every few million years, the planet cycled between humid coal ages and dry collapse ages. During the wet periods, swamp forests thrived, locking away more carbon and lowering global temperatures. During the dry spells, droughts killed vegetation, releasing that trapped carbon and warming the planet again. The Earth was caught in a self-destructive rhythm, a natural pendulum that swung between ice and fire. These shifts didn't just shape the environment, they reshaped life. Amphibians, once the dominant vertebrates, began to suffer as wetlands disappeared. Their eggs and skin couldn't handle the dryness. In their place rose a new class of animal, the reptiles with scaly skin that sealed in moisture and eggs protected by shells. Fossils of the earliest reptiles, like Hylonomus, appear right at this turning point, proof that climate chaos was rewriting evolution. The seas also took a beating. Nutrient flow changed as the ice melted and then refroze. Warm water stayed still, oxygen levels dropped, and whole marine communities broke down. There used to be a lot of trilobites, but not anymore. Coral reefs were destroyed by large-scale bleaching events, leaving behind empty limestone plains. The large eurypterids lost their weak hunting grounds as the bogs dried up. Even the air changed. When glaciers locked away huge volumes of water, global humidity fell, thinning the cloud cover. The once damp jungles began to dry. Dust storms swept across newly exposed plains, covering plants in grit. Some fossilized leaves from this time show signs of abrasion, evidence that winds carried sand strong enough to scar vegetation. This world was the Carboniferous in its last act. It was a dangerous place where balance had been lost. The things that used to make it lush are now tearing it apart. Fire destroyed forest after forest. Ice smashed the land. And when the thaw came, floods wiped out everything that had been left. When night fell, everything moved. In the Carboniferous, daytime was already pretty creepy, with thick mist, steady drips, and the buzzing of bugs. But the bush looked very different at night. It wasn't quiet when it was dark. It made things move. After sunset, almost all of the hunters, scavengers, and survivors came to life. The dense fog and dim light from lightning and swamp fires made the woods a living tide of movement. Things crawled, hissed, and ate in the dark. There was little true daylight here. The massive canopies of tree ferns and club mosses blocked most of the sun, leaving the forest floor in twilight even at noon. As night came, the temperature barely dropped, and the air stayed thick and warm, perfect for nocturnal life. Many Carboniferous creatures evolved to exploit the darkness, using vibration, smell, and moisture instead of sight. Fossil skulls of early amphibians show large, forward-facing eyes and expanded inner ear canals, clues that they were night hunters, attuned to tiny ripples and faint sounds. Under the cover of darkness, amphibians like Predatory crept from the rivers, their wet skin glinting in the firelight of distant smouldering trees. Giant millipedes moved in slow processions over fallen logs, scraping moss and fungi with mandibles that clicked rhythmically. And above it all, the air pulsed with wings. Enormous dragonflies like Meganeura, crickets the size of mice, and beetles whose shells caught stray flashes of lightning. Scientists studying the structure of fossilized eyes from this era have found something remarkable. Many insects and amphibians had large optical facets, features that help creatures see in low light. This means that night wasn't just a refuge, it was an entire ecosystem. While daylight belonged to fire and heat, the night belonged to stealth and sound. Every sound in this world meant something. The constant drone of insects acted like a background hum, masking the approach of predators. Frogs croaked deep, echoing calls that reverberated through the waterlogged air. Early crickets stridulated, rubbing their hardened limbs together, creating metallic clicks that signaled territory or mating. The soundscape of the Carboniferous night would have been deafening. A million overlapping frequencies in the dark, like a forest-sized orchestra that never stopped playing. And yet, silence did come. But only when something big was near. Fossil trackways suggest that massive amphibians like Eriops often hunted under moonlight. Their heavy bodies left wide drag marks and impressions where they paused to lunge. Smaller creatures likely froze in place at the first vibration, knowing that movement meant being seen, or felt, by something larger. In a world without mammals, amphibians were the apex predators of night. Pools and bogs glowed faintly in the dark, not with light, but with movement. Swarms of decaying plant matter released gas bubbles that rippled across the surface, confusing prey that mistook them for predators. Methane occasionally ignited into flickering swamp fires, brief blue flares that lit the canopy from below. For any creature living there, firelight meant danger, but it also drew insects by the thousands, creating feasts for flying hunters. Arthropods owned the night more completely than any other group. Some scientists believe that the first true nocturnal dominance of insects evolved here, driven by the dense plant cover and the threat of daytime fires. Carboniferous fossil layers even preserve traces of synchronized hatching cycles, suggesting that certain species timed their emergence for dusk, overwhelming predators through sheer numbers. The darkness also shaped evolution in unexpected ways. Amphibians that hunted by touch and sound developed stronger jaws and broader skulls to catch prey without seeing it. Insects evolved sensitive antennae that could detect heat and airflow, like radar before radar existed. Over millions of years, this nocturnal arms race created some of the earliest examples of sensory specialization, adaptations that would later define reptiles, birds, and mammals. Paleobotanists think that this beat was shared by all living things. At night, when it was cooler and stiller, some tree-sized plants let out their seeds. Layers of spores that are very dense in the fossil record often line up with ancient cycles of nighttime humidity. This suggests that the ecosystem was beating to a circadian beat, with life moving with the darkness instead of against it. Carboniferous forests are very dark at night, so you wouldn't be able to see much, but you would feel everything. The ground would shake as it moved. As people breathed, the air would hum and move. Around that area, something big would move in the bushes, and all the small animals would stop moving at the same time. The sound of the jungle, constant hissing and clicking. There was never a moment of silence in the Carboniferous jungle. Imagine being knee-deep in a hot swamp with plants the size of trees and moss-covered tree stumps all around you. The air was so thick with humidity that you could hear things miles away, put noise in the air by making big bugs hiss, claws scrape against bark, and wings and armor click over and over again. It wasn't a calm wild. As a group, they managed to stay alive. Paleontologists and acoustic biologists have reconstructed what this world might have sounded like based on fossilized insect wings and body structures. The evidence points to one conclusion. It was deafening. Giant crickets and katydid ancestors rubbed their hardened legs and wings together to produce piercing rhythmic calls. The frequency of these sounds, estimated from wing vein patterns, fell in the same range as modern insects, around 3 to 5 kilohertz, but at far greater volume, amplified by the dense, humid air. In the Carboniferous, sound didn't fade easily. It echoed. Even the smallest creatures contributed. Beetle-like insects drummed their abdomens against hollow roots to send vibrations through the ground, an early form of communication. Giant millipedes scraped their armor against bark as they moved, producing a constant dry rasp that mixed with the rustling of ferns. Every movement made noise. Every breath was part of the chaos. The soundscape had purpose. For some species, it was about claiming space. Early katydid fossils show specialized sound-producing ridges that may have worked like territorial calls, warnings to other males. Others used noise to attract mates, and predators learned to exploit it. Fossilized amphibians and arthropods with enlarged ear bones or vibration sensors suggest that listening became a weapon. In a jungle that never slept, hearing could mean the difference between catching dinner or becoming it. The forest itself added its own soundtrack. Dripping water, wind rushing through massive fronds, and the low rumble of collapsing trees created a background rhythm. The ground was alive too. Roots creaked, bubbles of gas popped from mud, and unseen creatures splashed through puddles. It was a soundscape of constant motion and danger. Massive dragonflies, Meganeura, make a low hum when their wings beat. This would have been one of the most recognizable sounds. A single bug could make a bass-like drone that could be heard all over the forest. When hundreds of them swarmed through the air in the evening, they made an echoing song that filled the sky with noise from dawn until dusk. The fire made its own roar. The atmosphere was full of oxygen, which made even small fires loud. When the trees caught fire, the cracking of wood and the hissing of gas made sounds like thunder that could be heard for miles. Charcoal layers found in fossils show that these fires happened often. Animals that lived nearby must have learned to recognize the sound as a warning to run away. Modern analogues can give us a clue to how loud this world truly was. In tropical rainforests today, ambient sound levels average around 60 to 70 decibels, about as loud as city traffic. Scientists estimate the Carboniferous could have reached 80 to 90 decibels during peak insect activity, equivalent to a passing subway train. For creatures that relied on vibration and sound, this meant constant overload. Every species had to tune its senses just to filter out the noise. Communication evolved into an art in this chaos. Some amphibians croaked at lower frequencies to be heard over the buzzing of insects. Others used the ripples in water instead of air vibrations to send words by hitting on objects. It's likely that the first complicated forms of communication, like bird songs, frog calls, and insect mating signs, started here, in this crazy jungle of noise. At night, the sound didn't stop. It changed. The high-pitched whirring of day gave way to deep, pulsing drones. Massive amphibians exhaled booming calls across the swamps, and nocturnal insects took over the treetops. Some scientists speculate that the Carboniferous jungle produced round-the-clock acoustic competition, where silence was rare and only predators brought temporary quiet. The smell of rot and death. Close your eyes and take a deep breath in the Carboniferous bush. The smell would be the first thing that hits you, not the heat. The air was thick, sour, and wet, and it smelled like rotting food. There weren't any flowers, fruits, or fresh grass, or pine smells yet. Everything that was alive was either growing, burning, or breaking down. There was a lot of rot on the ground, and the whole world smelled like a huge pile of compost. At the time, Earth was covered in dense swamp forests, endless green stretching from horizon to horizon. But these forests didn't recycle themselves like modern ones do. The planet's decomposers were still primitive. The bacteria and fungi that break down lignin, the tough material in wood, had barely evolved. As a result, when trees fell, they didn't rot properly. They piled up, layer after layer, turning into thick mats of half-rotted trunks and ferns. The process released gases like methane, carbon dioxide, and hydrogen sulfide, filling the air with a constant stench. The smell would have been overwhelming. Paleobotanists studying ancient coal seams say the Carboniferous world was essentially a giant composting system, producing chemical odors from decay on an unimaginable scale. Hydrogen sulfide smells like rotten eggs. Methane has a sharp, swampy odor, and together, mixed with the damp heat, they would have coated everything. Every breath tasted faintly metallic. Every gust of wind carried the scent of wet death. Amphibians and insects thrived in this environment because they didn't need clean air. Their lungs and trachea were simple, adapted to low oxygen and heavy humidity. But larger animals, and especially early reptiles, had to evolve more efficient breathing systems just to survive in the suffocating atmosphere. Modern scientists think that this adaptation, born from necessity, paved the way for reptiles to dominate when the swamps finally died. Decomposition in the Carboniferous worked slowly, almost eerily so. Without advanced fungi, fallen trees could lie on the forest floor for decades, partly mummified, partly sinking into the peat. Fossil logs found in coal beds still retain bark patterns so perfect they look freshly fallen, even after 300 million years. That's how little they decayed before being buried. Instead of turning to soil, these trees fermented, releasing heat and gases as microbes tried and failed to digest their tough fibers. In some places, this fermentation may have raised local temperatures enough to create spontaneous fires, igniting the oxygen-rich air above. The swamps themselves were chemical traps. Beneath the surface, microorganisms released ammonia and sulfur compounds, which mixed with stagnant water to form pools of acid. The smell of these bogs was described by one geologist as the stench of 1 billion rotting lungs. Even today, modern peat bogs that resemble Carboniferous conditions give off similar odors. Only back then, the effect was global. There was also the smell of spores, which was very strong and bitter. Carboniferous plants didn't have flowers. Instead, they sent out clouds of tiny spores that covered the air. With lots of natural oils, these spores smelled like spicy pepper. They could make a yellow-green cloud that could be seen for miles during the breeding season. If they were breathed in, they could have irritated or allergic reactions, and small animals with weak lungs could have even suffocated. After fires, the jungle's odor changed again. Charred wood and chemical ash replaced the swamp stink, producing clouds of burnt resin and sulfur. Fossil charcoal layers show that these fires were frequent, sometimes burning underground for years. Each blaze sterilized the surface and left behind an even thicker layer of ash and decay for new plants to grow on. What's amazing is that the rot, gas, and fermentation built the world we live in today. Coal was made by the never-ending circle of death and burial. Every crack we mine now was once a forest that wouldn't die properly. When you breathe in the smell of burning coal, you're taking in the last echoes of the Carboniferous atmosphere, which smells like 300 million years of death. Living there would have been like being in a never-ending storm of life and death. Every step you took hurt, and every breath hurt a little in your throat. Every breeze brought a new smell: mold, sulfur, smoke, methane, and mud. The world was still alive, but it smelled like it was going to die. The birth of predatory intelligence. The Carboniferous wasn't just a big world, it was also a world of plans. Its swamps and woods showed the first signs of predatory intelligence a long time before animals or dinosaurs learned to hunt with teamwork and smarts. There, among the plants and dead trees, bugs and amphibians from long ago started to develop behaviors that went beyond what they were instinctively doing. Life wasn't just responding for the first time, it was making plans. The evidence starts small. In the fossil beds of Mason Creek, Illinois, and Joggins, Nova Scotia, scientists have found clusters of insect remains preserved together. Individuals of the same species, fossilized side by side. These were not random deaths. Many appear to have died during coordinated movements, possibly during mass hunts or migrations. Some paleontologists propose that Carboniferous arthropods, especially mantid-like and roach-like predators, may have hunted in loose groups, surrounding prey in waterlogged clearings or under fallen logs. Predation at this time was already advanced. Large amphibians like Areops and Proto-mammals used ambush tactics, hiding in dark pools and lunging upward at anything that moved. Fossil skeletons show forward-facing eyes and strong neck muscles, signs of depth perception and strike precision. But smaller creatures were evolving something different: cooperation. In the insect world, size wasn't everything. Timing was. Coordinated swarms could overpower prey much larger than any single insect could handle. Recent computer models based on Carboniferous ecology suggest that swarming behavior may have originated here, not as defense, but as offense. Fossil wing fragments of early rochoid insects show uniform wear patterns, as if they spent long periods flying or gliding together, colliding mid-air in large numbers. This clustering could have been an early form of pack coordination, a behavior still seen in modern dragonflies that hunt in teams to drive prey toward water. Even predators were learning how to be patient. The frog Crassigerinus was a snake-like hunter that was found in Scotland. It had short legs, but a strong, flexible body that made it perfect for hiding in deep water. Its fossilized skulls showed that the inner ear bones grew in an uneven way, which suggests that it had advanced sound sensing. This let it stay still and silent until its prey came into its strike zone. The animals of the time were also very smart. To catch their food from above, giant dragonflies like Meganura probably hid in the warm air above forest clearings and waited to drop on them. Their complex eyes had almost 30,000 facets that let them precisely track movements, which is how modern visual hunting works biologically. Scientists looked at how big their brain cases were compared to how heavy they were, and found that, for their time, they had some of the most powerful brains among arthropods. In simple words, these bugs were smarter than they needed to be. This was a sign that predators were starting to value not only strength, but also intelligence. There's also evidence of trap-building behavior. In certain fossilized forest floors from Europe, researchers have uncovered symmetrical burrow networks consistent with ambush hunting. Some of these are thought to belong to early arachnids, ancient relatives of spiders and scorpions, which may have built primitive hiding pits. They likely sensed vibrations through silk-like threads or body hairs, lunging when prey passed. This marks the earliest known form of planned attack, where a predator used its environment as part of its weapon. Amphibians too were learning to adapt to prey behavior. Trackway fossils from the East Kirkton Quarry in Scotland show amphibians following zigzagging routes that mirror those of smaller animals, evidence of pursuit hunting. Instead of random wandering, they were following trails, possibly using chemical or tactile cues. These were the beginnings of what biologists call predictive predation, the ability to anticipate where prey would go next. All of things changed because of this quiet shift. Predators had a long-lasting advantage when they had intelligence, even in small amounts. The first animals that learned to plan or work together survived longer, had more babies, and passed on their skills. Stealth versus awareness, strategy versus defense. This was the start of the evolutionary arms race that still drives life today. If you could watch a Carboniferous night unfold, you'd see it in motion. A cluster of mantid-like insects creeps across a log, moving in rhythm. Below, a small amphibian freezes as ripples betray something larger in the water. A dragonfly shadow passes overhead, adjusts mid-flight, and swoops. None of this is random. The collapse of the green world. For almost 60 million years, the Carboniferous world had seemed to last forever. It was a place with endless lakes, huge woods and ferns that reached the sky, but nothing stays the same forever. About 305 million years ago, the system that had kept this green paradise running started to fall apart. The environment dried out, the oxygen levels dropped, and the huge forests that used to cover half the Earth died. It was more than just the end of an era. The green world died, and it was one of the first great extinctions on Earth. The collapse began quietly. As the continents of Gondwana and Euramerica drifted closer, they collided, forming the supercontinent Pangaea. This collision raised massive mountain ranges, the early Appalachians and Hercynians, which changed global wind and rainfall patterns. The once tropical belts that had supported the coal forests began to fragment. Swamps drained, rain became seasonal, rivers dried into floodplains. With less humidity came the first major drying event in Earth's history. The waterlogged ecosystems that had fed on constant rainfall began to starve. Tree-sized ferns and lycopsids, the dominant plants of the Carboniferous, could not survive drought. Their shallow roots, evolved for swampy soil, left them helpless when the ground hardened. Fossil evidence shows mass die-offs of Lepidodendron and Sigillaria, the forest giants that once towered over everything. In some layers, the abundance of their spores drops suddenly to near zero, the geological signature of extinction. Less oxygen was in the air when woods were cut down. Photosynthesis had been going at full speed for tens of millions of years, and oxygen levels were close to 35%. But now that the plants were gone, the air changed. Around 15% oxygen was present in the early Permian, which was less than half of what animals in the Carboniferous were used to. In the denser, drier atmosphere, many species, particularly big insects and amphibians, struggled to breathe. They slowly died of suffocation, their swollen lungs going from helping them to hurting them. The fires came next. With the drying climate and leftover oxygen, the dead forests burned on a scale no one had ever seen. Charcoal deposits in Europe, China, and North America show layer after layer of ash, entire regions consumed by flame. These fires released carbon dioxide back into the air, worsening the greenhouse effect and driving further drought. The planet had built its own trap: too much life, too much oxygen, and then too much flame. The loss of vegetation reshaped everything. Rivers silted up without roots to hold the banks. Soil eroded into the sea, clouding the water and killing marine ecosystems. Trilobites, already in decline, nearly disappeared. The coastal swamps that once produced endless coal turned into open plains dotted with scrub and sand. The coal age was over. The extinction wasn't just about plants, the entire food web collapsed with them. Amphibians, dependent on wet environments to breed, faced disaster. Fossil evidence from this time shows a sharp decline in amphibian diversity, especially the large predators like Eriops. In their place came the reptiles, creatures with tough skin and amniotic eggs that could survive away from water. The fall of one empire became the rise of another. Scientists call this event the Carboniferous rainforest collapse. In some places, it may have wiped out up to 70% of all species. It was one of the most important turning points in Earth's biological history. It was when the planet went from being dominated by swamps to surviving on dry land. Instead of the lush, oxygen-rich jungles, there are now sparse pine forests and fern fields. The sound of the never-ending bug music stopped. The nights got less noisy. Once sticky and thick, the air became sharp and dry. Even though there was a lot of damage, evolution kept going. Small snakes and lizards learned how to survive in the dry new environment by saving water and controlling the temperature. Because there was less air, insects shrunk, making the relatives of beetles, cockroaches, and crickets today. Life was changing again. It was trading plenty for endurance. Modern coal seams are the gravestones of this world. Each one marks a forest that died and never returned. Every chunk of coal is compressed sunlight from the Carboniferous, locked away when the green world falls. The legacy of the nightmare. The world that came after the Carboniferous looked nothing like the world that came before it. The woods that never ended were gone. The air became thinner. Big things like dragonflies, millipedes, and forest trees that had marked an era were lost under mud and stone. Their story didn't go away, though. It became a part of the earth. There is a ghost of that lost nightmare heaven in every piece of coal, puff of smoke, and spark of fire in a modern city. The Carboniferous didn't really die, it just changed. The thick black seams of coal beneath our feet are the fossilized remains of the Carboniferous forests. Millions of years of pressure turned their spongy, waterlogged peat into dense carbon rock. Every time we burn coal today, we're releasing ancient sunlight captured by ferns and trees that fell 300 million years ago. That energy, the same that fueled the monster insects and swamp fires, now powers human civilization. The age of steam, electricity, and industry was built on the bones of that green world. But the Carboniferous left more than energy behind. It left blueprints for ecosystems, evolution, and climate itself. The collapse of its forests reshaped life permanently. When the amphibians fell, reptiles rose to take their place, leading eventually to the dinosaurs, birds, and mammals. The oxygen crash that followed forced smaller, more efficient creatures to evolve lungs, circulation, and metabolism that could handle thin air. In a strange way, our ability to breathe today, our very endurance, traces back to the end of that era. The Carboniferous also taught Earth a lesson in balance. Too much life can be as dangerous as too little. The runaway growth of forests pulled so much carbon dioxide from the atmosphere that it triggered an ice age. When those forests died and burned, they released that carbon again, flipping the planet into warming. It was the first time in history that life itself changed the climate, a cycle that continues to this day. The Carboniferous is often used as a warning by experts today who study climate change. It showed that carbon can't stay buried forever. What's buried comes back up into the air in the end. Today, every mine and power plant opens up that old feedback loop again, letting the lake's air reach the sky. The Carboniferous didn't just make our energy, in a way. It put us in a tough spot. Even the ghosts of its creatures linger. The dragonflies still fly, though smaller now. The cockroaches that once ruled the canopy crawl through our cities. And the amphibians that croaked in the Carboniferous night have descendants still clinging to ponds and rainforests. The forest may have fallen, but its children survived in miniature. A quieter, humbler version of the world that came before. The marks can also be seen in the scenery. In places like Joggins, Nova Scotia, the cliffs still show fossil trees that stand straight, with stone limbs that stick out of the rock like tombstones. You can still see the diamond-shaped preserved bark marks of the lepidodendron tree in coal country in Britain, Germany, and the United States. This is the tree that made the oxygen in the world. Paleobotanists sometimes get a faint but real whiff of old peat when they break those stones. It's like the Carboniferous breathing again after 300 million years. The legacy of that nightmare isn't only in fossils or fuel, it's in the story of adaptation, the proof that life, no matter how strange or unstable, always finds a way forward. From the choking gases of the swamps came creatures that learned to breathe better. From the chaos of floods and fires came species that learned to endure drought and heat. and from the fall of one ecosystem came the birth of another, setting the stage for every age that followed. You would only see flat plains, cities, farms, and highways where those woods used to be if you could stand there now. You might even be standing on a tiny layer of coal, which is the memory of that world that you have long since forgotten. Atoms that were once part of those old trees are in the air you breathe, the electricity in your home, and the steel that shapes your life. The Carboniferous may be long gone, but its echoes still shape our world, in the coal we burn, the air we breathe, and the life that survived its chaos. It was a paradise that destroyed itself, a warning written in stone that even nature can go too far. If you enjoyed this journey into Earth's most terrifying chapter, hit like, subscribe, and keep watching, because the next world that rose from these ashes was even darker.